Hey everybody, it's Ripley back again. Today we're going to talk about numerical or approximate integration. I'm going to give you 3 techniques for doing this. Now, why do we need a numerical or approximate integration? Well, I'm guessing that a lot of you have had this niggling thought in the back of your head about an integral that can't be solved analytically. Like, for example, if I take the integral of sine of x squared, believe it or not, this is an innocuous enough looking integral, right? It's not too scary, but there's no way for me to solve this. I can't do it. Another example would be the integral of e to the x cubed dx, something like that. Can't do it. I'm stuck. So, well, we're not totally stuck. What we can do is we can use our methods, our Riemann sums, or our approximation methods that we learned right at the beginning of integrals, if you recall, to be able to approximate these values. Not only can we approximate these integrals, but we can get as close as we want to the actual value. Now, I'm going to keep this simple. Actually, to be able to do a numerical or approximate integration, you have to have a definite integral. You don't have a choice, right? Because an indefinite integral always spits out an antiderivative. And this function has no working antiderivative that is exactly its antiderivative. Isn't that weird? That to me is just crazy. All right, so let's keep it simple. I'm going to take the integral. Let's go the integral from 0 to 4 of sine of x squared dx. Okay? Now, there are 3 main techniques for doing the integral, for a numerical or approximate integration. And those are the midpoint, or the MRAM, right? MRAM, which we've seen this written before as M sub n. There's also something called the trapezoidal, and I'll explain that here in just a sec. Approximation, which is we'll call this T sub n, and then I'll explain something called Simpson's approximation as well. All right, which is S sub n. Now, what we're going to do is we're going to let n in all 3 of these cases be 8. Now, you may say, wait a second, Ripley, remember we had LRAM and RRAM, right? Remember those guys back when we first, this is the left rectangular approximation method, and the right rectangular approximation method. Well, if you recall, what we determined was that the MRAM is the Goldilocks sweet spot of rectangular approximations, right? Because left and right gave over or under approximations. So it's pretty much decided by convention that MRAM is the way to go. All right, for this example, we're going to do n equals 8. So just as a refresher, let's do m sub 8. We'll do it down here. M sub 8. Okay, how does this work? Well, first thing, as always, every single time, we find delta x. Remember that delta x is b minus a over n, which in this case, I get what? 4 minus 0 over 8, which tells me that delta x is 1/2, right? So I know that m sub 8 is going to be, now remember how this guy works. Let's just for giggles, and I forgot to type this thing up, get it prepped for us, but it doesn't take but a second. Let's take a look at what sine of x squared looks like between 0 and 4. Sorry for the delay. Shouldn't take but a minute, and that's enough of a oh man, I didn't even get to take a water break. That's all right, I'm going to do it anyway. All right, go away. Clearing everything out. Go away. Sorry, I was drinking water as I was clearing stuff out. I'll forget about it. Let's go up here. We'll clear that out, and we'll clear that out. Sorry about that. I should have done this housekeeping before, but that's okay. All right, we're going to go ahead and do sine of, and we're going to go x squared. Right? Oh, we better check to make sure that we are in radian mode. Go away. All right, mode. Cool, we're in radian. So let's go ahead and zoom. Let's go ahead and graph this. But let's mess with our window. Since we're between 0 and 4, let's go ahead and make our x min 0 and our x max 4. Let's make our y min -2, just so we can frame this thing in nicely. And our y max 2, and then we'll graph it. All right. Cool. I mean, that's kind of cool. That's what it looks like. Now, what we've got is, it's hard to see because we got a little, I think we got a little 1, 2, 3, 4. No, we don't. What we're going to do is we go, since we've got a delta x of 1/2, well, here's 1. So remember, we go to the middle of that first subinterval, right? So I'm sorry, we've got 8 subintervals. Let's try this again. Don't listen to me. Let me go back here. What did I say? Yeah. this is 1, 2, 3, 4. So we're going to go, our delta x is going to be 1/2 wide, right? And then we go, what is that? And then we go to the middle of that, which gets us to 1/4. Okay? So if we're going to have 8 subintervals, we start at 1/2, we go to the middle, and then between 1/2 and a full, we go to 3/4. Between 1 and 1 1/2, we go to 5/4, etc., etc. And if you recall from back in the day, the technique is we're going to go, let's go 1/2 times. Now let's think about this. Between 0 and 1/2, the midpoint is going to be 1/4, right? So I'm going to go sine of 1/4 squared. Now, how do I get the next one? Now, there are going to be 8 of these, true, because I've got n equals 8. So what's the next one going to be? Well, I simply add 1/2 to 1/4, or 2/4 to 1/4, and I get 3/4, right? So this becomes sine of, good Lord, I got all kinds of things popping up on me today. This is going to be sine of 3/4 squared, plus, if I add 2/4 to 3/4, I get 5/4. So sine of 5/4 squared, plus sine of 7/4 squared, plus, and then I told you guys that if you want to, after 3, since we don't want to write all 8, we're going to go dot, 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 plus, now what do we got here? What's going to be the last 2? It's easier for me to work backwards, right? If I go 4 minus 1/4, or 16/4 minus 1/4, right? Because 4th is the middle. I would get, what would I get? I'd get plus over here, sine of 15/4 squared, right? And then if I subtract 1/2 from that, or 2/4, I'd get sine of, it's kind of hard to do that. I don't know, that's weird. 13/4 squared. I could also count up from here, right? I go 7, 9, 11. So I'd have 1, 2, 3, 4, and then 9 would be 5, 11 would be 6, 13 is 7, 15 is, and we're good. And that's how that works, okay? And then out spits a number. Now I went ahead and cooking showed this number, and poof, out pops the number, which is 0.891378. We'll just call it 0.891. Okay, approximately equal to that guy. Basically, I popped everything in, if you notice up here, popped everything in, ended up with this number right here. Now, while we're here, because this is kind of important, let's go ahead and take a gander at what the actual integral is, because remember, our calculator can do this integral, which kind of begs the question, how does it do it? Well, that's actually pretty simple. I'm going to go from 0, let's see, I got to up toggle, I can't do enter, can I, to 4 of, and I go sine of, I got to go x squared. This is always a pain in the butt because I got to remember to stick that in there, even though it looks like it shouldn't be there. Hit x, hit enter. So the actual value of this is approximately 0.747. So we're off. However, the question is, how did the calculator do it? Well, believe it or not, the calculator did exactly what we did, only it did it with more n's. It took a whole bunch of n's until it got to this limiting point, right? It kind of like, remember Newton's method? With Newton's method, it keeps going and going and going until it gets repetition of digits. And once you get to repetition of digits, you know you can lock in. And I've got this thing locked in at what, 8, 9 digits? 1, 2, 3, 4, 5, I guess it's 10 digits. Okay, that's pretty cool. In other words, what we're doing right now is actually what the calculator does to solve numerical integrals. All right, that's what it does. It goes through this process. Now, there are algorithms there are probably mnemonic algorithms that help do it much more quickly. Now, that's done. We got our MRAM, right? We've got our midpoint approximation method. Let's talk about trapezoidal method and Simpson's method here for just a sec, and we'll see how they do. And I'll cooking show it as well, so you don't have to sit through me doing all the approximations. But first and foremost, let's talk about. That's fine. Let's talk about how trapezoidal approximation works. It's real simple. Let's take f of x. This is going to be any f of x. So let's bust this thing up. This is going to be. Well, this is going to be from A to B. Let's just make this 1 and this 2. Now, what mathematicians, they're always trying to dial it in a little bit better. What they said was, okay, rectangles are great. They seem to work fine. But what would happen if we took trapezoids? In other words, if I took the left-hand side of an interval and the right-hand side, and I let those guys be beta. That is just really badly drawn, isn't it? Let's go back real quick. Sorry, guys and gals. Wow, I cannot draw a straight line this morning. That's fantastic. Let's get rid of this. Maybe not enough coffee or green tea, maybe too much green tea. All right, boom, back to here. So I end up with a trapezoid that looks like that. Now, build another trapezoid that looks like that, and then add them up. Now, you got to remember, what we're trying to do is find the area, and hopefully you recall that the area of a trapezoid is simply, what do? We take the height, we divide it by 2, and then we take the sum of the bases, right? Base 1 plus base 2. And if we look at this, this would be base 1, and this would be base 2, right? But you should also notice, let's say that that is the area of 1, so we'll call this A1. Now look at, if this is A2, let's call this base 3, then A2 would be H divided by 2 times base 2 plus base 3. So I've got this repetition of base 2 in both of my trapezoids because this base 2 acts as the base of both A1 and A2. Does that make sense? All right. So let's come up with a T sub n formula before we try it with this function. So let's see, what's height? Well, wouldn't this be the height? If you were to take this thing and turn it on its side, you'd have a trapezoid that looked something like this, right? This would be base 2, this would be base 1, and over here would be delta x, wouldn't it? Which is just b minus a over n, right? This is delta x, which in this case is also the height. So what do? Well, if I want to do T sub n, this is equal to, I take delta x, which is h, I divide it by 2, and then I've got the very first value here, right? So I'm going to call that f of x sub 0, right? And then what do? I add this. So look, this would be x sub 0, this would be x sub 1, this would be x sub 2, etc., if our function went on considerably longer. Well, notice again that b sub 2 got used a whole bunch of times. Let me change colors one more time, and I'm going to add 2 more trapezoids in here. So instead of doing the blue, what I would have is I'd have a trapezoid here, I'd have a trapezoid here, I'd have a trapezoid here, and I'd have a trapezoid there, wouldn't I? So notice this base would be used in this trapezoid and this trapezoid. This base would be used in this trapezoid and this trapezoid. This base would be used in this trapezoid and this trapezoid. Now, notice the endpoints do not get used twice, only the interior values. So the way that we write this is delta x over 2 times the quantity, this is T sub n, by the way, trapezoidal approximation with n intervals, subintervals. I would end up with f of x sub naught plus twice f of x sub 1 plus twice f of x sub 2 plus plus twice f of x sub n minus 1 plus f of x sub n. Now, it's important to notice something here because this is actually going to resonate through Simpson's approximation as well. Notice what happens. If in this case with the greens, I have 1, 2, 3, 4 subintervals. So if I was doing this T sub 4, how many values would I have? Well, I would have the f sub 0, f of x sub 0, f of x sub 1, x sub 2, x sub 3, x sub 4. Because I'm including that x sub 0, I would have 5 values that go in here. So I would end up with n plus 1 values that go in here, wouldn't I? So T sub 4 would actually require, I'd have delta x over 2, I would do f of x sub 0 plus twice f of x sub 1 plus twice f of x sub 2 plus twice f of x sub 3 plus f of x sub 4. 1, 2, 3, 4, 5 values to get T sub 4. All right, so that's important because that's going to screw you up because before I was like, well, I had 8 values. Why did I have 8 values? Because it was m sub a. Well, not so much with trapezoidal, okay? Trapezoidal is a little, well, it's clunky, no doubt. Well, all of these are clunky, but the trapezoidal method is it's a little bit goofy, and you'll see that it's not as accurate as either Simpson's or the midpoint approximation method. So let me write this up, and then I'll cooking show this thing real quick, and we'll get it squared away. So I know that T sub 8 is going to be, well, we know that delta x, what did we say delta x was? It was 1/2. So I would take 1/2 divided by 2, okay, which we know is 1/4, but I really like writing those things out. Okay, now I'm going from 0 to 4, so I know that my delta x is 1/2. So this would be sine of 0 squared. I'm going to write the whole thing out. You're going to hate me for it, but that's all right. Not the first time, right? Plus twice, I move over delta x, so this would be sine of 1/2 squared, plus twice sine of 1 squared, plus twice sine of 3/2, or 1/2 squared, plus twice sine of 2 squared, plus twice sine of 5/2, or 2/2 squared, plus twice sine of 3 squared, plus twice sine of 7/2, or 3/2 squared, right? 7/2 squared, plus sine of 4 squared, right? And how many terms do I have? 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I'm good. Now, I'll be right back with my little cooking show thing so that you don't have to suffer through me doing this. See you in a sec. And poof, here's my cooking show solution. This is approximately equal to 0.517. Now you may say, whoa, Ripley, that's a huge difference, right? This is quite a bit of difference, right? It's almost 60% different from here to here. But whoa, 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 go easy. Remember, the actual value is 0.714, and this is 0.517. So the MRAM gave us an over approximation. The T sub 8 gave us an under approximation. Okay, which is okay because they're pretty close to the actual solution for only 8 subintervals. Let's talk about Simpson. Simpson's doesn't take a whole lot. It's a little complicated, and the actual proof of why the thing works can get kind of out of hand. But let's just take a function really quickly. I'm not going to do the full proof of it, but similar to the trapezoidal rule, what we do is we cut this thing up into subintervals, right? So let's just do 3 subintervals. Oh, I can't do that. Let's do 4 subintervals. You'll see why in just a sec. All right. Now, here's what Simpson said. He said, wait a sec. These geometric formations are super clunky. Why don't we use something that we know is a little less clunky, like polynomials? Can't I use a polynomial to approximate a chunk of this curve, like a quadratic? Why, instead of using these, these angled, these cornered geometric formations like rectangles and trapezoids, why don't I use something a little smoother, like, say, a quadratic? So why can't I fit a quadratic? Yeah, that's a terribly drawn quadratic. Why can't I fit a quadratic in here, right? So I would have this quadratic might go here. I've got another quadratic that would go here, something like that. I'd have a third, let's see, might as well go with the ugly green. I might even have a quadratic that went like this, right, for this guy right here. And then last but not least, I'd have another quadratic that was like this. Something like that. Now remember, quadratics, after they figured out areas on a curve, they were super easy to figure out what those areas were. So I could find the area under that quadratic right there, and then I could figure out the area under this quadratic right here, and then likewise all the way down the line. Now there's going to be still going to be over approximations and under approximations. However, notice how I'm picking up a little extra with this guy, and I was a little under with this guy. However, it appears that we can get a lot closer to the true value in a numerical sense. Well, what we gain in accuracy, we lose a little bit in simplicity. So let me show you the formula for this guy. So let's try that again. S sub n, Simpson's approximation with n subintervals. So S sub n is this guy. And I'm not going to go into the proof of this. It's a fun proof, but it takes a long time, and I know you guys don't want to sit through me proving the heck out of this thing. So this is one of those formulas. It's important. It doesn't show up very often. So if you would like to go into the theory of it with me in class, I would be happy to do so. What we do is we take delta x, and we divide it by 3. All right, and then, now you're like, 3, wait, where's that come from? Again, it comes from the proof of it, so just kind of deal with it for now. What this turns into is I've got f of x sub 0, just like trapezoidal, just like MRAM, except I'm not starting in the middle. I go plus, now this is where it gets a little bit weird. It goes 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3 plus 2 f of x sub 4 plus ... plus 2 f of x sub n minus 2 plus 4 f of x sub n minus 1, whoops, that should be an n minus 2, n minus 1, and then plus f of x sub n. So the thing to remember is always this. Here's the way I remember it. I always remember it as 1, 4, 2, 4, 1. In other words, I start with the coefficients of these f terms goes 1, and then it always goes 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So you've got to have, basically, there's the symmetry of this thing. I got to start and finish with a 1, and then the second and the penultimate coefficients are always 4, and then it repeats. Now what this tells us, notice, in this case, this would have been for n equals 4. What this does tell us with Simpson's is that n must be even. Must be even, which is very convenient because we're doing an s sub 8 for our integral of from 0 to 4 of sine of x squared dx. All right, so n's got to be even. So let's write this thing up. We already know that delta x is 1/2. Remember, delta x in this case is 1/2 because it's 4 minus 0 over 8, affectionately known as the half. So I go 1/2. I divide that by 3. I know it's a sixth, but it's helpful to do this, right? And then we'll write out some terms. I know it's going to be sine of 0 squared plus 4 sine of 1/2 squared plus 2, I'm not going to make you suffer through, well, maybe I will, 2 sine of 1 squared plus 4 sine of 1.5 or 3/2 squared. You can do decimals on this stuff. I hate decimals, but they work pretty well. 2 squared plus 4 sine of 2.5 squared plus, let's see, what do we got here? Plus 2 sine of 3 squared plus 4 sine of 3.5 squared plus sine of 4 squared. Now let's count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice, very much like trapezoidal, if you've got an even number of subintervals, which you have to be able to use Simpson's, then you absolutely are going to end up with an even number plus 1. You'll end up with n plus 1 values in here. Because you're counting, think of it this way, you're counting both endpoints, as opposed to just counting values within the subintervals like we did with rectangular approximation. All right, you know what? Let's go second entry and see if I can edit this thing. If I screw it up, I promise I'll cooking show you back to the. Yeah, I'm gonna cooking show you. You guys, I'm gonna make errors. I can just feel it in my giblets. So I'll meet you guys back here. All right, and the cooking show value is 0.572, which is approximately, of course, 0.572 or 0.571730, blah, blah, blah. And all I did was just went back in here and made an error, made a couple errors twice. But I just went in and I edited what I put in from the trapezoidal. Just changed the 2's to the 4's, changed the 1/4 to 1/6, and I was off to the races. Okay, so that's how Simpsons work. Whoa, now that's how, let's go back here. That's how Simpsons work. Now, what I'm going to show you, if you notice, let's see, remember the actual value of this, if I go, let's see if I can clear a few of these out. So, well, I'll just go back. It's easier to do it this way. No, so I can quit. Sorry, you guys. If I go second entry, where's my integral? I have my integral in here because we're clearly off, right? It's clear that there's an error. So I want to go back and find my integral. You know it's in here. Where'd you go? Where'd you go, you little monkey? Oh, man. Come on. It's in here somewhere. Ah, there it is. Okay, enter. Bam. All right, so this is the actual value, 0.747. So we'll go back over here. We know that the integral, this guy right here, is approximately equal to 0.747. And I told you guys, I made a mighty bold statement at the beginning of this lesson, and I said that we can actually figure this out we can figure this integral out to whatever level of accuracy that we want, depending on how big we went with n. Now, the way we're going to do that, and this is going to make everybody a little bit crazy because this is new and different, is we're going to come up with something called an error bound. There are three types of error bounds, and I'm gonna try and be as brief with this as I can because this video is definitely getting pretty long. But it's important that you know how these things work because they're not that scary, even though they look really scary. Let's talk about error bounds. So if I'm going to do the error bound for the trapezoid, now this absolute value of E sub t, don't let it scare you. It's a name. All that this means is it means error for trap approximation, for trap approx. That's all it is. Okay? So there's a formula. The error for the trapezoidal. We know that this is always going to be less than or equal to. In other words, if we do the trapezoidal approximation, the error for it is always going to be less than or equal to this equation. Now, I'm going to explain this k in a sec. Don't be afraid. This is b minus a cubed over 12n squared. Now, this k is referred to, excuse me, as I know that k is going to be the least upper bound, if possible. It's some value, it's some constant that is greater than or equal to the absolute value of the second derivative of x, or of f, excuse me. So let's see how this plays out with our integral from 0 to 4 of sine of x squared dx, right, where we let n equal 8. So we have t sub 8, and I forget what we got over here. What was our t sub? There's s. We're over here with Simpsons. Where was n? T was 0.517. All right. So this was approximately equal to 0.517. All right. Now, what's the first thing that we got to do? Well, I got to figure out what k is. I know that f of x is equal to sine of x squared, right? So I know that f primed of x is equal to 2x cosine of x squared, right? Because of chain rule, derivative of sine of blah is cos blah d blah, which spits out 2x. The second derivative of x is equal to, this is a product, right? So product rule gives me 2 cosine of x squared. Now, plus 2x times negative sine of x squared times 2x, which is affectionately known as 2 cosine, sorry about that, guys and gals, 2 cosine of x squared minus 4x squared sine of x squared. Now, recall what we're doing here. We're trying to solve for a k, some constant that is going to be greater than or equal to, excuse me, the value of this second derivative. Now, it needs to be noted strongly that we're not talking about the value of this derivative, because if you think about what the behavior of this function, this thing blows up at infinity, right? Or actually, it goes to negative infinity, doesn't it? So this would be on the interval from 0 to 4. So we're only talking about the interval on which we're talking about. Now, I was nice enough to do a little cooking show with you guys. Pow! And this is, if you look real quick, y equals, it's 2 cos x squared minus 4x squared sine x squared, right? Now look at my window, because I jiggered with this thing just a little bit. I'm going from 0 to 4 because that's my interval, and then I played with it, and I get y min between negative 60 and 50, and y max is 50 with a y scale of 10. That just makes it prettier to look at. And then when I look at it, this is what it looks like. Now look, so my function's between negative 60 and 50 on the interval from 0 to 4. Well, is it relatively obvious that negative 60 is definitely greater than or equal to the absolute value, or not negative 60, positive 60? Right? Because we're talking about the absolute value. So this would flip over. I mean, if I wanted to, I could put this whole thing in absolute values, but I think you guys get the deal. So in this case, I'm going to let 60 be k. Now, if I really wanted to be fancy, I could figure out what the max, or what the min in this case is, right? Because it's negative, and I can cruise over, and I could let that be exactly, remember, the more accurate I am, come on, cruise, dang it. This thing does not want to play. Let me see if I can toggle over. This thing wants to fight me, you guys. Well, I'm committed at this point. Come on, go, 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 go. Go, go, go. That's one thing about the interface with this thing. It's kind of a pain in the butt. So I want to get as close to the min as I can get. Did I get past it? Yep. You know what? Ah, dang it. And now it woke up. So let's just say positive 60 is going to be our k. You may say, well, Ripley, why isn't it negative 60? Well, because k is greater than or equal to the absolute value of the second derivative. So this is going to imply that k is equal to 60. Now, had my calculator not been a pain in the butt, excuse me, I could have found the exact minimum value at that point if I go back here, which was over down here, but then, yeah, right? I can use my calculator to find the exact min down here, but we don't have to be that anal. The more accurate we are, the closer, the smaller the error bound is. So let's go back to this. I know that the error bound, when I use a trapezoidal approximation, is going to be less than or equal to 60 times 4 minus 0 cubed over 12 times, well, what was n? That's 8 squared, right? So this is going to be 60 times 4 cubed over 12 times 64, which equals, let's go over here, let's go back to our calculator, might as well use it while we're here. Let's go set and quit. And what did I say? 60 times 4 cubed, scooch over, divided by, I got to use parentheses, don't I? I got to go, let's see, what is this? 12 times 64 in paren, and I got to take this bad boy and I got to square it. And let's see, does that look right to everybody? Enter. Bam. Look at that. That's crazy. That tells me that my error bound, how far off I am with those 8 approximations in the trapezoidal, is going to be less than, let's see, this implies that the error bound with trapezoidal approximation is going to be less than or equal to, what did that say again? Getting old. 0.00651. 0.00651. That's pretty cool. All right, let's do the error bound for the midpoint. All right, so I've got my midpoint here. Remember though, let's go back over this. Had I found the exact min on the interval between 0 and 4, took the absolute value of that, it would have been slightly smaller. A smaller k here, it being k, a smaller k here means a smaller k here, smaller k here. This number would have been slightly smaller. So the more precise I am in finding that k, the more I actually know what my error bound is. If I could have let this be 300, but then my error bound wouldn't have been as accurate, I wouldn't have been able to figure out exactly how accurate I'm being, excuse me, with my trapezoidal approximation. Now remember, what this means is my trapezoidal approximation is within 0.00651 of the actual value of the interval itself. That's pretty neat. Okay, let's do the error bound for the midpoint. It's exactly the same thing, only I get k, whoops, this is going to be less than or equal to k times b minus a cubed over 24 times n squared. Now, if you look, that's a 12, that's a 24. Hey, guess what? The midpoint has an error that is half as much, so it's twice as accurate. So I don't even need, this implies this is going to be less than or equal to, let's keep with 60, times 4 minus 0 cubed over 24 times 64, right? Which is just going to half this value. So what's that going to be? That's going to be 0.003, what is that? 255? 255. That's pretty cool. All right, now you're begging the question. Let's see. I know it's there. All right. Oh, well, we'll get back to that. What about Simpson's rule? Now, Simpson's rule is, I forget the expression, a fish of a different, colored pelt. I don't know what it is. It's a cat of a different color. No, it's not that. All right, what it is it's k times b minus a. Now, this time it's to the fifth. Now, remember, the proof of these is quite a bit beyond the scope of what we're able to prove at this point. This requires real analysis. I actually proved these in my analysis courses, and it's a nightmare. However, that said, they're super useful, especially when you're doing numerical approximation. You end up with, now instead of 12 or 24, we end up with 180, but it's n to the fourth. Now, think about that. Before we had 12 and 24, and we had n squared down here, right? Remember back here? I had my n squared. But with Simpson's, I've got n to the fourth, which means as long as this difference isn't huge and this k isn't huge, I'm going to get a tiny, tiny error. Now, there's a difference. You pay for that tiny error by virtue of k. In this case, k is going to be greater than or equal to the absolute value of the fourth derivative of x, which can be a bit of a nightmare, okay? So what we do in this case is we're not going to take the fourth derivative of our function, sine of x squared. I'm going to cheat. I'm going to take the integral from 0 to 4 of, you're going to be like, Ripley, you're such a wimp. And I'm going to say, you know what, you're absolutely correct. I'm not actually going to do the s sub 8 for it because you guys would all revolt. But let's say this equals some number. All right, now you may also say, well, Ripley, I can take this. I know that this is e to the x from 0 to 4, which is e to the 4 minus 1, right? We know that. We can do this by hand. But just for the sake of instruction, just bear with me for a sec. I want to find out the error bound. Well, the first thing that I would have to do is I would have to find the fourth derivative of e to the x. Well, thank God, we know that the fourth derivative of e to the x is e to the x. Yay! All right? Now remember, we're talking about this. We know what e to the x looks like. It looks like this. Well, damn! Right? And we go out here to 4, and we know that on the interval from 0 to 4, the biggest value that it achieves, we know that k would equal e to the 4th, right? It's not that, now it could be e to the 5th. It could be, let's see, e to the 4th, what is that about? About 81, right? A little less than 81. I can make it be 100. But the more precise I am with my k, the more accurate I am with my error bound. So I know that the error, using the Simpson's approximation when n equals 8, is going to equal e to the 4th times 4 minus 0 to the 5th. Now this is a little bit bigger than the last one, isn't it? Remember in the last one we had them cubed, right? In this case, we're going to the 5th. But we make up for that because we've got 180 times 8 to the 4th. Now, let's crank over to our calculator real quick. I'm going to take, all right, let's go. This is always a pain in the butt. We're going to go second. E to the 4th. And then we said times, excuse me. Let's see, what do I got to do? I got to go times 4 to the 5th, right? 4 to the 5th. I hope that I don't have to put a times in there. We're about to figure that out, though, aren't we? Divided by pren, and I've got 180 times 8 to the 4th. And I move over, and I in my pren. Let's see what we get. Pow. See if I get an error. Yay. All right. Now, so you may say, wait a second, Ripley, look at the differences in errors. But remember, this error was for sine of x squared. This is for e to the x. So this tells me that if I do a Simpson's approximation on e to the x, on the integral from 0 to 4 of e to the x, then I will always be at least within, what was my value again? Some kind of top, 0.0758. Whoops, this is going to be less than or equal to, right? 0.0758. Simpson's is the most accurate. And the reason it is because that denominator is always going to be bigger than this denominator and this denominator because it's got a 180 times n to the 4th. Now, you may say, but what about this cube versus raised to the 5th? Well, you're right. There's a juggling act there. One of these may be more accurate if b minus a is really, really big, right? If it's huge, all right, and n is small. But as always, what happens if we want to be more accurate? What do? We let n get bigger. We let it grow, all right? Which really begs the question, and this is kind of a fun question. What if I wanted, how big should I let n be? If I wanted my Simpson's approximation of the integral from 0 to 4 of e to the x to be within 1/10,000th. So let's say that I want my error bound for my Simpson's approximation to be less than or equal to 0.0001, right? Tens, hundreds, thousands, 10,000s. How big should n be? How big should n be? In other words, how many subintervals should I take? Well, the easiest way to do that is to simply solve for n in this inequality. Make it an equation. So I go 0.0001, right? is equal to, now I know that k is going to be e to the fourth, right? It doesn't matter. The fourth derivative of e to the x is always going to be the x, and on 0 to 4, the maximum value of that, the absolute value, in this case they're the same thing, is going to be e to the fourth, right? Times, now I go 4 minus 0 to the fifth over 180 times n to the fourth. Now, I'm going to solve for n. So I cross multiply, right? I get n to the fourth is equal to e to the fourth times 4 to the fifth over 180 times 0.0001. True? So what this really is e to the fourth times 4 to the fifth times 10,000, right? 1/10,000th, divided by 180. Now you're going to be like, Ripley, that's a huge number. Yeah, but remember, that's n to the fourth. Let's figure out what that number is. So I've got, let's go back to my handy dandy calculator. I've got second e to the fourth times, what I say, 4 to the fifth times 4 to the fifth, right? Times 10,000, and 1, 2, 3, divided by 180. Right? Look at that. That's insane. That's 3,106,028.091. Yeah, but now I got to take the fourth root of that. So if I stumble back over here, this, I got, well, let's do this. This is equal to big number. So if I want n, what was that number again? Dang it, I'm being lazy, aren't I? Let's see if I can see it here. 3,106,028 approximately. Approximately. 3,106, what was it, 028? 028, yeah, 028.091, which implies that n is equal to the fourth root, get away, go away, bingo, is equal to the fourth root of 3,106,028.091. Let's see what that is. Use a calculator, and I'm going to go second answer to the, and I know there's a simpler way to do this, but I'm old school, to the 1/4, enter. 41.98. Now, so let's go back here. So n is equal to 41.98. Right? Was it 41.98? Does that sound right to you guys? Whoops. 41.981. So go back here, 0.981. Now think about this. Go away. There. So think about that. N is equal to 41.981, but I can't have a fraction of a subinterval. So this implies that n is equal to 42. Whoops, not 49, 42. All right, now we got lucky because n ended up being even. Let's say just for giggles, I'll change the color to red so that we know that this is not really true. But let's say just for giggles, in this case, that n equaled 42.981, right? So we're like, oh, Ripley, well, you can't have a fraction of a subinterval, which implies that n is equal to 43. And I go, wrong. I would use this colored pen on a test because it's Simpson's. And Simpson's always has to be even. So that would imply that n is equal to 44. It's easy. That's super useful, isn't it? That's super helpful. Now, I'm not sure what your calculator does. I'm not sure if it uses these error bounds in its algorithm and its computation to determine how many n's it needs when it actually does the numerical integrals for you, or if it just goes through these approximation methods until it gets repetitions of values. All right, anyway, that's for us to discuss another time. Go away. That's for us to discuss another time and in class. I hope this was helpful. Sorry it was so long. This is a beefy theoretical section, so those have a tendency to take a long time. Thank you for your time and attention. Have an absolutely wonderful day, and I'll see you in the morning. Bye-bye.